Hello all, this is Monica and welcome to my presentation on the research paper MapReduce Simplified Data Processing on Large Clusters. Moving on to the contents of this presentation, there is motivation, basic concepts, problem definition and challenge, related work, proposed approach, contributions, validation, conclusion and future work. So, the motivation behind this research paper is in recent years, there has been an exponential growth in the volume of data generated across various domains. With the internet, sensor devices, social media, and other digital technologies such as blockchain, there is variety of data that not only needs to be stored but also to be analyzed to make future improvements. So, why do we need this data? What do we do with this data? And why is this important? To perform large scale graph computations, for sorting, for developing data mining and machine learning algorithms, and to prevent data loss. All of this for advancement in technology. We need this data. So, where do we use this analyzed data? What are the real world applications of this data? So, in companies like Google, hundreds of optimization programs are implemented and executed on large clusters each day. This improves the performance of Google's search engine service while avoiding data loss. Not only Google, other companies such as Amazon, Yahoo, and Bing also use large scale data analysis. Companies such as Yahoo and Bing use this data analysis to index and rank web pages, improving the relevance and accuracy of search results. Online retailers like Amazon and Netflix utilize massive datasets to personalize recommendations for users, enhancing user experience and driving sales. Also, in social media, platforms like Facebook and Twitter and Instagram analyze huge volumes of user generated content to understand user behavior, sentiment analysis, and trend detection. Also, in other domains such as healthcare, we use the large datasets of patient records, medical images to improve diagnosis, treatment plans, and public health initiatives. So, moving on to the basic concepts discussed in this research paper. So, the first basic concept is fault tolerance. Fault tolerance is a capability of a system or component to continue operating properly in the event of failure or malfunction of one or more of its components. Fault tolerance is designing system with redundancy, error detection, and recovery mechanism to ensure uninterrupted operation. Parallelism. Parallelism refers to the ability to execute multiple tasks or operations parallelly to improve performance and efficiency in computing systems. In parallelism, tasks are broken down to smaller subtasks that can be executed independently across multiple CPU cores or distributed nodes in a cluster. So here we can see pipeline parallelism, where tasks are divided into stages with each stage occurring parallelly. Scalability. Scalability refers to the ability of a system to handle huge workload or data efficiently with high quality performance. So, the basic concepts, the MapReduce function. So here we need a programming model or library that can process data parallelly and optimize it locally. MapReduce is one such programming model that has been introduced in this research paper by Jeffrey Dean at Google for processing and generating large datasets. The key components in this MapReduce function are the map function, which processes input key value pairs to generate intermediate key value pairs, and the reduce function, which merges intermediate values associated with the same intermediate key. So it maps K1 and V1 values, let's just say, and then it gives out a list, which is the input for the reduce function. And this generates a list V2, which is then given to the output file. So moving on to the problem definition and challenge. What is the problem over here? So we need to develop a programming model and implement it for efficient processing and generation of large datasets on distributed system. The input here is the key value pairs representing the data to be processed. The output is process key value pairs representing results for computation. So what is the objective over here? We have to automate parallelization, fault tolerance, data distribution, and load balancing for large-scale data processing on distributed systems. What are the constraints in this problem? The constraints are scalability, as discussed. It should handle large data sets. Fault tolerance, it must be resilient to machine failures. It should be easy to use and high performance. So what is the challenge over here? The data must be distributed and analyzed where we have a huge input in data. It should be optimized locally and it should handle system failure, which is the most important key concept over here. As it handles system failure on time, the computational time gradually reduces and then thus delivering a high quality output. Moving on to the related work discussed in this research paper. So the related work has been precisely described in this research paper by the authors. One is the bulk synchronous programming, which was introduced in the early 1990s. It provides higher level abstractions for parallel programming, facilitating easier development of parallel programs. Also, message passing interface offers primitives for communication and coordination among distributed processes, which is used in scientific computing. These two have addressed parallel programming challenges by then, but these two require explicit handling of parallelization, whereas MapReduce incorporates automatic parallelization and fault tolerance. Active disk. Active disk emerged in late 1990s and 2000s. It improves I/O performance, but these are not high-level programming models such as map reducing. Also, Condor, which is a cluster management system, also shares similarities with Google's infrastructure. This is also not a high-level programming language programming model as MapReduce. Challenge system employs eager scheduling mechanism, but this does not have automatic fault tolerant mechanism. So unlike MapReduce, which is tailored for large scale data processing, these traditional data processing systems lack few things such as fault tolerance or handling failures or large data sets. So, awareness of related work is clearly stated in this research paper by authors. MapReduce has made an assumption of restricting the program model so that it could handle errors. If this assumption is removed, it may lose simplicity and ease of use. So, what is the proposed approach? What is the new approach that has been discussed in this paper, which is different from the approaches that have been implemented earlier? So, moving on to the approach. So, here we can see a user program, a master, and workers. So, what is this? We can see the input files are divided into different split tasks, and multiple copies of the program are started on a cluster of machine. So what is new in this approach is the master copy. One copy or one system acts as a master while the rest are workers, which are assigned map or reduce tasks. Map task read input data, apply the user defined map function, and buffer intermediate key value pairs in memory. This is locally written, as you can see here. Buffered pairs are periodically written to local disk and partitioned into regions. Reduce task retrieve buffered data from this map function. The whatever the output is, it is given to the reduce task. and sorted by intermediate keys and apply the user's reduce function. The output of the reduce function is appended to the final output file after each reduce partition. Upon completion of all these tasks, the master wakes up the user program and the map reduce calls control to the user. So why we are assigning master in this? This MapReduce incorporates master data structures. The master stores the state of the map and reduce tasks, which is idle, in progress, completed, and identity of worker machines. For each completed map task, it stores the location and sizes of the intermediate file regions produced by the task. So, how do we solve the previous problems or challenges that we have discussed earlier? So, in case the worker failure occurs, how does the master recognize it? The master pings every worker periodically if the work is done or not. If no responses is received from a worker in a certain amount of time, the marks the worker as failed. Any map task completed by the worker are reset back to the initial idle state, and therefore it becomes eligible for scheduling on other workers. Similarly, any map task or reduced task in progress on a failed worker is also reset to idle. So this worker also becomes eligible for rescheduling. So fault tolerance is hence solved in this map reduce. So what if the master failure occurs? It is easy to make periodic checkpoints for the master such that as we discussed, there is master data structures inscribed here. If the master task dies, a new copy can be started from the last checkpointed state. So, as there is only one master, this situation is most unlikely to occur. So, how do we solve the problem of large scale machine failures? So this MapReduce function is resilient to tolerate large-scale failures. For example, during network maintenance, the master re-executed work done by unreachable worker machines or the failed machines to other workers to complete it on time. So this ensures the completion of MapReduce operation. So, what is new in this approach is also the importance of backup tasks, which is highlighted by the authors. Backup tasks are employed in MapReduce to address the issue of stragglers, which are machines that significantly prolong the completion time of a data analysis or data processing. To mitigate this, the master schedules backup executions of remaining in progress tasks near completion, marking tasks as completed. Like once a task is completed, the master makes sure task is marked as completed, which is done either by the primary or the backup execution. So, this exemplified a 44% longer completion time observed when we disable this backup task. But when the backup tasks are enabled, the execution time is much faster. So what do we do if if there is bugs in the user code? So bugs in the user code are pretty normal, but map or reduce function can crash on certain records. So this typically skips them to ensure forward progress such that the progress does not stop for one bugging. So additionally, debugging and testing purposes, an alternative implementation of MapReduce library allows sequential execution of all work on a local machine. This can also facilitate debugging, profiling, and small-scale testing with user-provided controls. So moving on to the contributions of this. So what are the contributions, valid contributions of the MapReduce function? So now the MapReduce is stored in a library. So this is not part of the complex program that the user provides. So the indexing code is simple, small, and easy to understand and deals with fault tolerance, distribution, and parallelization. So there's a specified library for this. So this avoids extra process over the data. The indexing process has become much easier to operate because problems caused by machine failure, slow machines, and network hiccups are dealt automatically by the MapReduce library. So what are the common examples what are the example functions in this MapReduce library? So distributed grep. Distributed grep is one such function which emits a line if it matches a supplied pattern. Count of URL access frequency. This is used by search engines to process logs of web page requests and output with how whatever the count is. For if suppose the count is 1 or 2, it returns the count. Reverse web link graph. It outputs target source pairs for each link to a target URL found in the named source. Term vector per host. This emits hostname when hostname is extracted from the URL of the document. And it is also used in sorting, data mining, and machine learning. So, what is the validation? How can we say that the MapReduce function really works? So, let's move on to the validation or the experimental setup set up by the authors to test the efficiency of the MapReduce function. So, here we can see the first three graphs are normal execution. These three are without backup, and this when 200 tasks have been killed. So, in the first part, we can see a normal execution of the sort program. It shows various graphs representing what three functions, which is input read rate, data sent over the network, and sorted data returned to output files. So this we can see that it typically takes from 900 to 1000 seconds to complete the data analysis. Let's say we have removed backup tasks during this process. So if you remove backup tasks during the execution of a sorting program, without backup tasks, we can see the authors have observed 44% of time increase compared to the normal execution. Also, when 200 tasks are intentionally killed by the authors to observe the performance of the machine, here intentional machine failures are introduced. So, this quickly restarts new worker process on the failed machines. Despite worker deaths, as the master reschedules the task to other workers, this this just shows slightly higher time than the normal executions, as you can see. So this shows that the MapReduce system handles different scenarios such as normal execution, failure of backup tasks, and intentional machine failures efficiently. So we can see the code redundancy has reduced due to the map reduced library, and redundant passes over the data has been avoided, and also it is much easier to operate because it reduces the problems caused by machine failures, slow machines, and working hiccups. Moving on to the conclusion and future work. So here, the MapReduce programming model, it simplifies parallelization, distribution, and fault tolerance. It facilitates management of computations across distributed system. It considers network bandwidth as an efficient network resource which needs to be conserved at any point of time. So it implements locality optimization and minimize data transfer and enhance efficiency. Also, during execution, it avoids impact of slow machines and handles failures, and ensures data integrity in large-scale distributed environments. So, what are the advancements that have been done after this MapReduce? There was Apache Hadoop, which was developed in 2006 after MapReduce, which is developed in 2003. Apache Hadoop, an open source framework, is used for distributed storage and processing of large data sets. This has HDFS, which is Hadoop Distributed File System for storage, and Yarn, yet another resource negotiator for resource management. Apache Spark, which is released in 2014, it is another open source distributed computing framework that extends beyond MapReduce by providing in memory data processing, iterative algorithms, and interactive queries. It has flexibility and performance, and it is popular for large scale data processing tasks. Google Cloud Dataflow, which is released in 2014 by the Google team itself, is a fully managed service for system for stream and batch processing of data on Google Cloud platform. TensorFlow is also developed by Google in 2015 for for machine learning framework developed by Google. It enables distributed training and inference of machine learning models on large data sets. Introduced in 2010, Google BigQuery is a serverless, highly scalable data warehouse designed for analyzing large datasets using SQL queries. These frameworks and services built upon the foundation laid by the MapReduce, providing more advanced and efficient ways to process large datasets for various use cases. So, what are the success factors of MapReduce at Google? So, ease of use. It abstracts complexities like parallelization and fault tolerance, and it was versatile for data generation, sorting, data mining. It addresses the diverse needs within the Google infrastructure. Scalability, it scales efficiently to large clusters with thousands of machines, and it is suitable for handling Google's extensive computational requirements. So these are the references I've gone through for researching my research paper. Thank you for this opportunity.